Hey guys, welcome to the fourth lesson on asynchronous programming using C#. In this lesson, we're going to be focusing on basic thread safety. Now, I'm emphasizing the basic word because I'm not positive yet. I think I'm going to do another video on thread safety going into a little bit more advanced topics. But just seeing this and looking at this basic thread safety video, you'll be able to build applications that are thread safe. So that's what I really want to emphasize. I might do another video depending on feedback from you guys. But like I said, this video will be a good video to watch on thread safety. Now, obviously, we need to start with, what is thread safety? Because if this is the first time you are programming asynchronously using possibly multiple threads, you probably never encountered these problems. And obviously, this whole series is on asynchronous programming, and because of that, because we're using asynchronous programming, this opens a whole new world of problems that we can run into. So one big problem that we're going to focus on is using asynchronous programming with data. And what I mean by that is if we have, let's say, two threads, if those two threads are targeting one piece of data, we can run into problems. Now, some problems may be more significant than other problems, but basically, if we have multiple threads targeting the same piece of data, we can get results that are unpredictable. And I'll show you what I mean by that. But if we have two threads and they're working on completely different pieces of data, they both have their own data that they're working with, then we'll never have any problems with thread safety. So because of that, one approach that people use to fix this problem is if we have two threads and we want to work on the same data, some programmers, and this all matters what you're working on, will make a copy of the data that they want to work and give each thread a copy to work on. And this allows, because the data is separate, this allows there to be no problems. But obviously, then you're going to have to do things at the end to maybe link them back together or whatever you're doing. I don't know. But that is one solution. And that works fine, but if we're dealing with lots of data, then we'll run into some problems with that. An example of this is word processing. Normally, this is a really easy example to see where the data is copied for each thread to work on. So if we have a word processor, normally the processing, let's say it's handled by one thread, like the actual input and typing into the word processor. But when I go and hit that print button, you can see it makes a separate copy, and that copy is used by one thread and the other copy is used by another thread. So in that case, it creates a copy so that we have no problems. If that helps clear anything up with making a copy. So let's go ahead. I'm going to go ahead and type in an example that's going to show us some of the problems that we can run into. And in this example, we're going to see a couple concepts. And one big concept that I want to point out is this idea of atomic operations. And I'll explain what that means once the example is typed in, which should only be a second for you. But in this example, we'll see why we can't have multiple threads targeting one piece of data. That's what we'll see in this example. Okay, so here's the example that we're going to look at to see what problems we can run in with having multiple threads accessing a same piece of data. So right now how this is set up, we have no problems. Basically, we have an integer called iterations that has a number, and then we have another int called numTasks that's holding 1. We have a list of tasks, and then an integer value that's equal to 0. The for loop is going to go over, and depending on how many number of tasks, which is only 1, so this only happening 1, it will create one task that will increment, called this function increment value, which takes in value, passes as a reference, which means if it's edited inside of the function itself, the value of it will carry over back when we get back to the caller in here. So if it passes in ref value, if value is changed inside the function, the value out here will be affected. All increment value does is, based off the iterations, it just goes and adds up to the amount of iterations using the basic for loop. So after we do that, so we create one task that does that, and then we add this task to our task array just for the point so that we can wait to make sure all the tasks are done by using task.waitAll, which says do not continue until all tasks are completed. And then once they're completed, then we're going to go ahead and display the expected value by using our math by just doing num tasks times iterations, which will give us the expected value, and then the actual value that we get from the tasks itself by going in and doing the adding, and that will be displayed in actual value. So if we run this now, we'll see that the two numbers actually do equal each other. So we have no problem right now, and the reason why we're having no problem is because we only have one thread that is actually doing this action. We only create a number, number of tasks is only one, so there's only one thread going out and doing the adding. So we're going to have, obviously, no problems. Now, the problems start arising when what happens if I add another task? If I say, oh, I want two tasks to do this now. So it's going to split up the work with two tasks. So now instead, when we create a task, only one task is going to go up to each individual task will go up to the iterations count. So they're going to both, hopefully, the expected value, the actual value should be equal to the expected value if we had no thread problems. So if we go ahead and run this, we'll see where the problems start coming. So ready, here we go. As we can see, the operation runs and our expected value is correct, but our actual value is not. If we run this again, we're going to see different results for the actual value every single time we run it. And you may be saying, why are we getting this unpredictable value? Because when we used one task only, we had no problem. But since we're using two tasks, if we did three tasks, let's say, we're still going to have a problem. That's the expected value and the actual value is what we're getting. They're completely different. They're not matching up. So the problem is our threads are accessing or manipulating this one piece of data called value. And they're manipulating this value through an operation. The operation is called value plus plus. It's an increment operator. The first thing to note about this is value plus plus is equivalent to saying value equals value plus 1. These two lines are equivalent. So let's use this one. This is what it's what it gets translated into. Now, this operation right here is not thread safe. And the reason why it's not thread safe is because it has multiple parts to it, and I'll explain this here in a second. There is, however, a type of operation called an atomic operation that is considered thread safe. Atomic operations are thread safe. And now I'm going to read you this definition that I think is really good to understand. This is one of the best definitions I've seen for atomic operations. And this author particularly says, an atomic operation is one that, from the perspective of observers, transitions states from one valid value to another valid value without the state having a temporary invalid value. So basically, all this is saying is an atomic operation is when we are transitioning from one valid value to another valid value. If in this transition there is not a moment that value is or that variable you can think of is in an invalid state. So it's never invalid. And that's important to note because in this, we have that problem. In an atomic operation, it can go, basically, you could think of an atomic operation. It can go from point A from point B in one move. It doesn't have to do multiple things. It's going A to B in one move. It's not, there's no time where from A to B that we're in some kind of invalid state. We're always in a valid state, and that's critically important. So because of that, if all our operations are atomic, like I said, meaning that it can move from point A to point B in one consecutive move, it doesn't need to ever do multiple things, and it's never going to be in a invalid state, then we are thread safe. You don't have to worry about anything if everything is atomic, and we'll see that here in a second. So now let's get back to the problem. Why are we getting a problem? Because with this right here. And like I said, the problem is because this operation is not atomic. Basically, if we look at this in more detail, there are several steps. We have an assignment, a read, and an add right here. So there's kind of three separate steps that is going on. And basically, the problem comes in this because when we are reading and assigning and doing all these different things, if we have multiple threads doing that on the same piece of data, there's going to be problems. Because if one thread is reading, let's say, value, while that thread is reading it, another thread could be changing it. So we don't know exactly what the value is. The computer is lost. So if, let's say, I have one thread that's saying, okay, increment value by 1. But the second thread is, well, okay, let's reword this. Let's say we have one thread who is doing this assignment, which is basically just this value plus plus. So we have a thread doing this assignment, value equals value plus 1. While this thread is reading the value, so let's say he got the value and it's 2, let's say hypothetically. When he's about to do the add, so 2 plus 1, another thread already did this, and now the value it was actually 3. So when this guy does the assignment, it's going to actually go down by 1. I don't know if you can see this. I don't know if I'm explaining this well. Let me try to break this up to hopefully allow you guys to understand this, because this is important. Let's hypothetically say that this is what thread 1 is doing, and this is what thread 2 is doing. Both are doing this operation. So let's say thread 1 is going first. Let's say we're starting off value is 0. So I come in and I'm trying to increment this. So let's say, okay, value, thread 1 starts. So value is currently 0. Value is 0. And obviously this is 1. So when it's going to do this add, what happens when, oh no, thread 2 came in and ran faster? So that means when thread 2 came in, we got a 0 here, a 0 here, and then a 1. But then this finished, and now value is equal to 1. So value is really equal to 1, but in thread 1, it still thinks that value is 0. So now when this runs, it's assuming value is 0 rather than it really being 1. So when this is done, now this will be 1. But it should really be 2. And the reason is because this ran faster than this one, so it updated, but it didn't actually count it because this is doing an assignment. It's going to take the 0 plus 1 and then assign it to value, so then we're going to get that 1 instead of it really being a 2. In reality, what would happen is, if this was thread safe and atomic, this would say, okay, 0, 0, 1. Okay, this equals to 1. And then when this runs, it would be, oh, 1, 1, 1. Oh, this is equal to 2. That's what should happen. But because they're going off in different times and it's completely unpredictable, we can get data that's not accurate. we're actually losing data. It could be doing some subtraction because of just the order that it's running. And now, because we have so many operations, this actually has an impact on it, and that's why we're not getting those exact values. Now, I'm trying to explain this the best I can, but this is hard to explain. So, if you guys have any questions on this particularly, I can explain it again, maybe in a separate video. But let me explain it one more time so that hopefully everyone understands. The problem is coming when we have multiple threads on the same data, because this operation value plus plus really is equal to this operation, and it has multiple states. So while one is reading, the other one could be, while one thread is reading the value, the other thread could be updating it. And if it updates it before, or if it updates it after it read it, but before it assigns, then it's going to be messed up. That's the problem. So to fix this, problem, we need to have some atomic operation that could fix it. And luckily for us, there is a built-in class called the Interlocked class. And the Interlocked class has some basic operations called increment, decrement, and add, which would respectively do what you would think they increment a value, decrement a value, and add two values together. But all these operations are atomic, meaning they are thread safe. They will happen in one action, in one movement. So there's no chance for any problems happening where one is reading and one is writing. It's all going to be one operation, so it's always going to be accurate. So to fix our problem, we're just going to switch this to using the Interlocked class. So we're going to say interlocked, and we need to resolve that. So interlocked.increment, and we're going to and it's going to take in a ref of the value. So we're just going to pass in the value, and this will increment it by 1 atomically. That is the most important thing to remember out of this. This will be incremented by 1, but atomically. This is equivalent to saying value plus plus, or value equals value plus 1, or value plus equal 1. These are all equivalent, but the major difference is that this is atomic, and the other one, this one's atomic and the other ones are not. So we have multiple steps in here, which having multiple steps in an operation when using multiple threads is not safe. This operation is atomic, so it's only one step. So it goes A to B. That's it instantly, so there's no chance for anything happening to corrupt this data. So this is atomic. So now let's go ahead and run this. And by running this, we should have a program that works. So let's go ahead and run it. And as you can see, everything is okay. Everything matches up. The actual value is the same as the expected value. Let me switch this back to 2 tasks. And let's try this. Now, one thing you definitely notice is that this is slower. And using the Interlocked class, obviously it's atomic, but it's slow when it has to fight against multiple threads. If multiple threads are trying to do it, it can be slow. That's the problem. This is one problem with thread safety that we have to deal with. But we're going to be looking at other ways of thread safety as well here in a second. But as you can see, using this atomic operation to increment the values, the expected value and the actual value will match up every single time, because we don't have to deal with the multiple steps of using a non-atomic operation. So the expected value is equal to the actual value, all because of this atomic operation. Once again, if I had value plus plus, this is not atomic, and if we run this, then we get that corrupted data again. And that's only because value plus plus is equivalent to saying value equals value plus 1. So if I ran this is still going to have the problem. And I told you the problem is because of that reading and writing and assigning. Or the reading, adding, and assigning. That's the problem. It's not one action. It's 3 actions. Whereas this atomic operation is only 1 action. And because of it, we always get the correct data. So this is good for operations that only utilize one piece of data. But what happens if we have 2 separate pieces of data, and we need to make sure that all these pieces of data are thread safe? Now, there are a bunch of ways to do this, and we're going to look at 2 of them here in this video, and then if I do an advanced video, we'll look at other ones that are in there, and there's other types of thread safety mechanisms and stuff like that we may go into. But for this example, we're going to first I'm going to sketch out this class called small business. And small business has a problem if it is being used by multiple threads. So let me go ahead and just do that real fast. It's going to be instant for you, but I need to type it out. Okay, so here's my class called small business. Now, small business has 2 operations that we need to focus on: receive payment and net worth. Receive payment takes in an amount, adds the cash by that amount, and then minuses that amount to receivables. And net worth is just your cash plus your receivables. So we have these 2 operations. So the problem with this is if we have 2 threads, let's say one thread is accessing or calling this receive payment, and one thread is calling net worth. The problem can arise where if we're doing receive payment and it only have executed cash plus equal amount, but it hasn't done this statement yet. So for here, let's say we are here, the thread is currently here, we executed this but not yet this, and then let's say the second thread is calling net worth. That means they're going to get an inaccurate representation of net worth because the receivable amount has not been calculated yet. Only the cash has been. So net worth is not going to be accurate in this if we have 2 threads accessing, one accessing receive payment and one accessing net worth. That is the problem that we need to deal with. So one way that we can fix this is using the monitor class. And basically the monitor class, how it works is when someone acquires the monitor, that means if any other thread is trying to access that data that the monitor is monitoring, they have to wait until the other thread that has the monitor releases that monitor so that the second thread can then enter that monitor. So to do this, we first need to create a object, and you can call this anything you want. I'm going to call it state guard, and this object is going to be used. This is what the monitors are going to monitor. So if the monitors are monitoring this object, then whoever tries to access that monitor has to wait. So let me just go ahead to do this. We have to say monitor on the code that we want to protect, monitor.enter, passing in our state guard. And then when we are done, we're going to say monitor.exit, passing in our state guard again. So that's on the data that we want to protect on receive payment. But then we also have to do this on our net worth. So let's go ahead and rewrite this. I'm going to say decimal net worth equals cash plus receivables return net worth. This is just so I could place the monitor. Monitor.enter state guard monitor.exit state guard. So basically what this is saying is if we have 2 separate threads, if the first thread gets to receive payment first, it will enter this monitor. Once this monitor is entered, until it exits, anything else that enters a monitor on this object, on this state guard, must wait. So if I get to this first on thread 1, I can execute these 2 statements freely, knowing that this statement will not go off until I am done, because this is protected by the same monitor on the same state guard. So if the two threads come in, if thread 1 comes in, if it enters this monitor first, it is going to be safe. We know while I'm executing this code, this will not be going off. It will be sitting here waiting. The thread will sit at this monitor waiting for this monitor to be released. Once this monitor enters this monitor.exit, then this monitor will then continue. So by doing that, we can protect ourselves. So right now, currently, this would work. We are thread safe. Our monitors are protecting ourselves. Our monitor is protecting us. Okay. Now, there's a problem with monitors that I'm not going to go into too much until maybe if I do the next video, because the monitor has a nice function that we can use if we want to use timing out with me. And we would only want to time out for certain problems, maybe a deadlock or something like that, which we'll look at in the advanced section if I do go into that. But then the other problem is, what if once I entered this monitor, what happens if the code that I'm executing inside of here throws an exception, and that exception causes me to never actually execute monitor.exit? That is one problem using monitor, and we could fix this by using a try and finally block, by basically saying try this code and always put a finally around this monitor.exit, meaning that no matter what, the monitor.exit will run. Because if an exception gets thrown here and monitor.exit never gets executed, this thread over here waiting to execute this code will be sitting there forever, because they're not ever going to be able to enter the monitor on that state guard. So because of this, and because of the crazy syntax that it requires to fix this problem, C# introduced the lock keyword to make this easier, that automatically handles everything. It will automatically, if an exception is thrown, it will make sure that the monitor or the lock is released. So the replacement for this is just going lock state guard, and then you put a block around the code that you want. So now that's locked, and then the same thing over here, lock state guard. Oops, I need that. Oops, let's try this again. So now by doing this, we are safe. We are still thread safe. This is the same thing as monitor.enter and monitor. Oh wait, this has to be. Now we are safe. Monitor.exit will be called even if an exception is thrown. Oops. So this is the preferred way, instead of using monitor.enter and monitor.exit. The monitor class is still handy though. If you want to use a timeout, or if you want to have a situation where timeouts can happen, and we may look at that in the advanced video. But for the most part, this is a good way to ensure thread safety, because this lock class does all the hard stuff, making sure that the lock is released and things like that. So this is the preferred way. We are thread safe here. Once one thread acquires the lock by entering the lock, if any other thread enters another lock, or maybe even the same statement itself, it will have to wait at the lock until the thread that acquired the lock releases the lock. So only one thread can have the lock at the same time, based off of the state guard that's passed in. Now, the question is, what should I lock? And in early days, people used to say, do this, lock this. And the problem with locking this is, yes, it will lock this current instance, but this current instance is a public instance. Anything that has access to this instance, maybe through a reference, by a variable outside of this class, If they acquire a lock on that, then we could have some problems. So we don't know who's acquiring a locks by using this. So the standard way of doing is creating a private object inside of the class that then we lock on that, because nothing else can lock that. We know what it will be locking it. So that is the safest way of doing it, by locking a private variable. So that is it for this video. We looked at the atomic operation and this whole concept of atomic operations using the interlocked class. And then we looked at the monitor and lock class, which are basically the same thing. The lock class is just a shorthand for the monitor class, because it's easier to write and it does all the hard stuff behind the scenes with ensuring the lock be released. So that is it for this video. Using this information, you can create applications that are thread safe. If I don't go into the advanced section, that will just deal with some other types of locks and other situations that we may need locking. But the next main topic that I want to cover is concurrent data structures. Basically, data structures that have thread safety built into it. So that will help us when dealing with collections of data. Because this thread safety stuff is still involved with collections. Let's say we have a list, a shared list, and we have multiple threads trying to access that list. If we have threads trying to add things to it and remove things from it, while other things are iterating over it, we can run into lots of problems with that. So concurrent data collections, concurrent data structures, can help us with that. That is the next major topic that I want to focus on. So that's it for this video. If you enjoyed it, give me a thumbs up, leave me some comments if you have any questions, and be sure to stay tuned for the next video.